Well, thank you very much, Jose, for that introduction. And it's a pleasure to be here. And as we begin, I'd like to thank Jose and Amir Pham for inviting me to give this presentation, which I've entitled Lowering Greenhouse Gas Emissions with FRP Composites. So we're going to be talking, let's move here, let's advance. We're going to be talking about decarbonization, and here is an outline of my talk. I'm going to talk about the decarbonization message for FRP, tell you a little bit about terminology, then show you some calculations and examples where I'm comparing FRP and steel, and examples where FRP is used in conjunction with concrete. I'll then talk about the decarbonization landscape and finish up with the take-home message. So we're going to be talking about decarbonization, and here's a little bit of terminology. Many people, many companies say that they want to decarbonize, but different people say it in different ways. Some people say they want to lower greenhouse gas or GHG emissions. Other people say, I want to lower my carbon footprint. Some people say, I want to lower embodied carbon. Others say, I want to achieve net zero. The point that I want to make here is that all of these statements are saying essentially the same thing. They all want to lower emissions of carbon dioxide. Now, people want to do that because carbon dioxide is the most abundant greenhouse gas, but it is not the only greenhouse gas. Gases like methane and nitric oxide are also GHGs, and each of those gases has a different global warming potential. So, for example, methane is actually 28 times worse than carbon dioxide. What you do is to use these GWPs to calculate what are called equivalents of CO2 emissions. And the most common unit you'll see is kilograms of CO2 equivalents. And you will see this acronym, kilograms of CO2e. You'll see that repeatedly during my presentation. This slide contains a figure that I really like. It comes from the Carbon Leadership Forum. And I like it because it shows all of the different stages in the life cycle of a building material. It shows the different stages, and it defines terms like cradle to gate, cradle to grave, cradle to cradle. It also contains these alphanumeric characters, which define the steps in each project or each stage. And I'll be using some of those alphanumeric characters during my presentation. And as I'll show here, most environmental product declarations, or EPDs, are what they call for the product stage, also known as cradle to gate. So I told you I'd tell you my take-home message at the end, but I'm going to show it now, and I'm going to show it repeatedly during my presentation. My take-home message is very simple, that the use of FRP composites can significantly lower emissions of carbon dioxide and other greenhouse gases in infrastructure and construction applications. You're going to see that that's true for cradle to gate. It's also true for cradle to grave. So let's jump into some decarbonization calculations and examples. So to do a decarbonization calculation, you need two things. You need a part weight and an emission factor. And the most common one you'll see in this talk is kilograms of CO2 equivalents per kilogram. There are many different sources of emission factors, and I'm going to use all of them in today's presentation. They come from the Carbon Leadership Forum, or the CLF databases that have been published in 2021 and 2023 and give you data for materials like concrete, steel, and aluminum. They come from ACMA, the American Composite Manufacturers Association, which has conducted life cycle inventories in 2012 and 2023 and provides data for FRP composites. You can get it from environmental product disclosures, and you can get it from life cycle assessments, or LCAs. The point that I want to make is you're getting information from multiple sources, different sources, and it's very important as you do these calculations that you do apples versus apples comparisons, where you're looking at the same life cycle stage, like A1 to A3, And it's very important that you watch the units as you do these calculations. As I've said, this is the most common one, kilograms of CO2 E per kilogram. But sometimes you'll see per metric ton. For concrete, you'll see per cubic meter. It's very important to watch the units. A little bit more about the CLF database. The CLF database provides data for steel, aluminum, concrete, and masonry. And I've copied part of the table here, which shows the emission factors for many different types of steel. It's important to note that FRP is not included in the CLF database. You have to go to other sources to get information for FRP. The CLF database gives you cradle to gate emission factors. Again, that's known as the product stage, or A1 to A3. Here is the data in this table, and it gives you the emission factors in kilograms of CO2 equivalents per metric ton. And again, be careful watching the units, because if you were to put this as per kilogram, this number would get divided by 1,000. And I also just want to point out, this data comes from this report. There's also a very useful appendix. The appendix is where I got that very useful figure from a few slides ago. It also shows you how they collect the data and do the calculations that they present in this table. Okay, so now where do you find emission factors for FRP? Well, they come from ACMA, which has published inventories in 2012 and 2023. Again, they are giving cradle to gate emission factors, which is the same scope as the CLF database. In 2012, they published an LCI that gave emission factors for unsaturated polyester resins, e-glass, and composites prepared by compression molding, vacuum infusion, and open molding. And in 2023, they published another report giving information for vinyl esters and pultruded composites. And this is the kind of information that you will find in those LCIs. What I've shown here is the table that shows cradle to gate emissions for vacuum infused composites. I'm going to use that in the girder calculations that I'll show you in a little while. Here you've got data for open molded composites, and I'm going to use that in the grading calculations that you will see very soon. You can also get emission factors for FRP from an EPD, and this is an environmental product disclosure for FRP rebar from Schock, which is a German company. I've copied this table here, and I'm just going to highlight two parts of it. First of all, we're talking about the product stage, and this is the same stage as in the CLF database for steel. And here are the kilograms of CO2 equivalents that I use for the FRP rebar calculations that you will see very soon. So, I told you that there was a take-home message. The use of FRP composites can significantly lower emissions of CO2 and other greenhouse gases, but actually there are two distinct sub-messages that I want to deliver today. First, that is true when FRP composites are used in place of steel, and secondly, when they are used in conjunction with concrete. Two different messages, and I'm going to talk about both of them. We'll start with steel. I'm going to give you 4 different examples of where FRP has been used in place of steel and results in lower greenhouse gas emissions. I'm going to talk about gratings, girders, utility poles, and rebar. Example number 1 has to do with gratings. They're also used in decking and railings. Materials like this, which are produced by companies like Amoco Seasafe and Strongwell here in the United States. These gratings, deckings, and railings are used in things like the oil and gas industry for offshore drilling. They're used in wastewater treatment, and they're used in inland waterways for things like handrails, gratings, and ladders. It's important to note that these gratings and deckings are 73% lighter than their steel counterparts, and they are much more corrosion resistant than steel, which is important because they're being used in very corrosive environments in these applications. So let's do our first calculation. This is cradle to gate emissions where I'm comparing FRP gratings to steel gratings. So I go into the CLF database, the 2023 version, and I get information for steel decking. Here is the emission factor, 2.32 kilograms of CO2 equivalents per kilogram. To keep the math simple, I've assumed a weight of 1,000 kilograms. You multiply these two columns together and you get 2,320 kilograms of CO2 equivalents. Then I come down here for the FRP grading. I go into the ACMA LCI for 2012. I use the data for open molded composites, which is how Amoco C-Safe makes their gradings. A higher emission factor, multiply by 270. Why? Because FRP is 73% lighter. And when you do the math here, you get 946 kilograms of CO2 equivalents. And if you compare those two numbers, you will see that the number with FRP is 59% lower than the value for steel decking. 59%. Let's do a second example. FRP girders. Some of you may be familiar with these G-beam girders, and they have been commercialized by Advanced Infrastructure Technology and used in bridges in Maine here in the United States and other states. The technology was developed at the University of Maine, and these girders are prepared by infusion with vinyl ester resins. Here's an example of a bridge that uses it in Maine. Again, these FRP girders are 70% lighter than steel girders, which makes them much easier to transport and install. And again, they are much more corrosion resistant than steel. Let's do a calculation for the girders. This time I'm taking information for plate steel from the CLF database, and I come up with 1,730 kilograms of CO2 equivalents. I go into the ACMA LCI database in 2012 for vacuum infusion, and I have to make one assumption here. I actually have to use unsaturated polyester resin as a surrogate for vinyl ester resin because this database does not include information for vinyl ester resins. But as a chemist, I am very comfortable with that assumption. I do the math. Again, FRP is 70% lighter. Instead of 1,000 kilograms, you've got 300 kilograms. You come up with 789 kilograms of CO2 equivalents, which is 54% lower than the value for steel. Actually quite similar to the number for the gradings. Let's do example number 3. I'm going to talk about FRP utility poles. And pultruded utility poles have been commercialized by Creative Pultrusions here in the United States. They're used in the vertical poles and in the cross arms. They commercialize them under the names Storm Strong and Fire Strong. The key attributes of these FRP poles are that they are lightweight, they're corrosion resistant, they have excellent dielectric properties, they're resistant to insects and rotting, and they are resilient. They've been able to withstand hurricanes, and they've been able to withstand fires. A lot of very nice benefits of these FRP poles. So let's talk about emissions calculations for those poles. And I've worked very closely with Dustin Troutman from Creative Pultrusions, comparing Storm Strong FRP poles and galvanized steel poles. And again, we're doing cradle to gate calculations here. What kind of data have we used? Well, Creative Pultrusions has actually created an EPD for their poles that has been prepared by BRE Global. And here is the data, the environmental impact data from that EPD. And here is the data for GWP and kilograms of CO2 equivalents that I have used in my calculations. For steel, we have used an EPD from the hot dipped galvanized steel from the American Galvanizers Association for hot dipped galvanized steel. And here is the data from that EPD, and there are the values that we have used in these calculations. So again, we're pulling data from different sources and doing apples versus apples comparisons. And here is the cradle to gate emissions calculations. Here is the calculation for steel poles that are FRP poles that are 50 feet long and what are called ANSI class H2. Get data from the steel EPD, data from the FRP EPD, you do the math, and these are the actual weights of the poles from Dustin. And if you compare the number for FRP to the number for steel, you see a 31% reduction with FRP. Let's take another comparison. This is for 45-foot long poles and what called ANSI Class 1. Again, you do the math, you get 616 versus 1142. That is a 46% reduction, 46% lower with FRP. Everything you've seen so far has been double digits. Let's do the last example, FRP rebar. I'm sure that many of you are familiar with FRP rebar. It can replace steel rebar as a reinforcement for concrete. It's used in place of epoxy-coated steel, stainless steel, and galvanized steel rebar. And it's used in buildings and bridges and seawalls. Again, it is 72% lighter than steel rebar and much more corrosion resistant than steel. But there are a couple of buts in this example. When you use FRP rebar, you need 20% more on a lineal foot basis relative to steel for the same stiffness, 20% more. And that comes from Steve Nolan at the Florida Department of Transportation. Another important point is that steel rebar is typically made with recycled steel. It is not made in a blast furnace. It is recycled steel processed in an electric arc furnace. And that is important when you do the calculations, because rebar made with recycled steel has much lower emission factors than other forms of steel. We come back to this table, and here is the data for rebar. I know it's a little bit hard to see. There are two different types, fabricated and unfabricated. But you see here values of 753 and 854. And they are smaller, considerably smaller than the other values in the rest of this table, which are typically between 1,000 and 2,500. And that has a significant effect on the calculations when you compare FRP rebar and steel rebar. Again, recycled steel. So let's do the cradle to gate emissions. You've seen this before. I'm taking data from the CLF database that I just showed you. I'm taking data from the shock EPD for FRP. I do the math. But before I do the math, I've got 616 and 854. Remember that FRP is 72% lighter, but per Steve Nolan, you need 26 more. So this 280 becomes 336. And now you're comparing the product of 739 versus 854. But it is still 13% lower with FRP than with steel. So the use of FRP rebar again results in a double-digit reduction in GHG emissions, but the reductions are lower when FRP is compared to recycled steel. So summarizing this portion of my talk, I've shown you that the use of FRP in place of steel results in double-digit reductions in greenhouse gas emissions. That's true for FRP prepared by a variety of different forming methods, and it's even true when FRP is compared to recycled steel. So the take-home message from this portion of my talk is that FRP has a very good cradle-to-gate decarbonization story to tell versus steel. So now let's switch gears. Now let's switch from steel to concrete. And again, I told you that there's a two-part message here, that you can significantly lower emissions of CO2 and other greenhouse gases. Now I want to talk about when FRP is used in conjunction with concrete. But before I do that, I'm sure that some of you are asking, why is it a two-part message? Why are there two parts to this message? Well, we have to go back to some calculations to explain that. Remember that to do an emissions calculation, you need weight times emission factor. And the emission factors come from the literature. And I've shown you things like these for plate steel and vacuum infused FRP. Okay? So here's a sample calculation. Again, 1,000 kilograms of steel times an emission factor, you get 1730. For FRP, which is 70% lighter, it's 300 kilograms times a bigger emission factor. Usually the emission factors for FRP end up between 2.0 and 3.0, so this is a very good example, and you get 789, which is less than half of 1730. You've seen this before. What you're seeing here is that the emission factor for FRP is higher, but the weight of FRP is much lower, and that translates into lower kilograms of CO2 equivalents with FRP. So the first message is that you can use FRP in place of steel to significantly lower emissions. But now let's talk about concrete, because it's a different story here. Okay. You all know that cement is used to make concrete, and that concrete is the most widely used construction material in the world. Some of you may know that cement production is one of the biggest emitters of carbon dioxide. And that's true because when you use calcium carbonate and you calcine it, you liberate a lot of carbon dioxide. But when it comes to emissions calculations, you have to remember that concrete is only 10% cement typically. And in a construction application, FRP is competing against concrete, not against cement. And that emission factor goes from 1 down to 0.1 kilograms of CO2 equivalents per kilogram. And that order of magnitude difference makes a big difference in the calculations as shown here, because now I'm taking concrete, multiplying it by 0.1, and I get only 100 kilograms of CO2 equivalents. FRP is typically 10 to 20% lighter than concrete. Let's take 20% lighter. Multiply it by the 2.2 that I used for FRP rebar, and the product is 1760. That is 18 times higher. With steel, this was a bigger number than this. With concrete, this is a much bigger number than the value for concrete. So you don't want to replace FRP with concrete with FRP if you want to lower CO2 emissions. You need a very, very different message than with steel. And message number 2 is that you can use FRP in conjunction with concrete to significantly lower emissions. I've entitled this slide an important equation for decarbonization. It's not a differential equation. It's a very simple equation. It's that concrete plus FRP is lower CO2. And why is that? Because using FRP enables you to significantly lower the amount of concrete you need. Using FRP with concrete can mean less concrete, which means less cement, which means less CO2. And I'm going to show you now that with 5 more examples during the remainder of my talk. Let's begin with the Hillman composite beam. This is a picture of the Hillman composite beam. This is a cartoon. I'll use the cartoon to explain it. It is a hybrid construction whose design involves embedded steel rebar in a concrete core that provides you compressive strength. And then you've got a thin outer section in an FRP shell, which provides tensile strength. And if you take this hybrid material, it ends up that a Hillman composite beam, or HCB, weighs 69% less than a precast concrete beam. So what you've got here is really an optimized use of each material. You've got concrete plus steel plus FRP, and that optimized combination gives you compressive strength, tensile strength, and lower weight. Now, in conjunction with RD Digital in the UK, CMSI, a Canadian composite fabricator, has conducted a life cycle assessment comparing a Hillman composite beam and a precast concrete beam. And here are the results of that LCA. What you've seen in this graph here is the kilograms of CO2 equivalents for the Hillman composite beam and a precast concrete beam. And what you see here is that the emissions of CO2 and other greenhouse gases are 42% lower for the Hillman composite beam, about 15,000 versus 24,000. 42% lower. Again, double-digit reduction. Why is that the case? There are two reasons. First of all, as shown in the blue bars, comparing the blue bars, you've got lower cradle-to-gate emissions in those steps A1 to A3. Why? Because the optimized design of the beam significantly reduces the amount of steel and concrete needed to produce the beam. That's the blue part of the bars. Then you've got the orange part, which really translates into lower transportation emissions. Step A4, the HCB is 69% lighter and much easier to transport to the construction site, and that reduces the transportation emissions by 69%. So overall, 42% lower. Let's go to another example. These are reductions in the amount of concrete cover, and I'm actually going to give two sub-examples here. The use of FRP rebar has enabled the Florida DOT to reduce the concrete cover in extremely aggressive environments. They are dealing with the Atlantic Ocean, they're dealing with the Gulf of Mexico, a lot of seawater. And this is a table of data from their structures manual, where they're comparing the steel cover requirements in inches to the FRP requirements in inches. And if you compare the two columns, the cover is always lower with FRP. What does this translate into? I'm going to give you two examples. First, reducing the concrete cover in a bridge deck that is prepared with FRP rebar. And this is an example where I've used data and calculations from Steve Nolan at FDOT for both steel reinforced and FRP reinforced concrete bridge decks. And this is what he has done an analysis on. And this table, or this graph rather, summarizes the results of his work, where you're comparing reducing the amount of concrete in a steel reinforced bridge and an FRP reinforced bridge. And what Steve's calculations have shown is that the bridge deck with FRP rebar weighs 15% less, and the bridge deck with FRP rebar uses 12% less concrete. So less weight, less concrete, and that means that CO2 emissions are also reduced by 12%. Less concrete, less cement, less CO2. Here's another very similar example from New Zealand. Here is reducing the concrete cover in a break wall with FRP rebar. Pultron has used FRP rebar in this break wall in this marina in New Zealand. Here's a picture of what the break wall looks like. And they have found that the weight of each concrete slab in the break wall was reduced from 15 to 13 metric tons. That's a 13% reduction in the amount of concrete, very similar to the numbers for the bridge deck on the previous slide. So you reduce the amount of concrete by 13%, you also reduce CO2 emissions by 13%. The next example is for the Halls River Bridge. This is located in Florida, north of Tampa. It's about 190 feet long. It was completed by the Florida DOT in November of 2019. And it uses all kinds of FRP materials. It uses FRP rebar. It uses these carbon fiber composite cables, and it uses Hillman composite beams. And the Florida DOT, in conjunction with the University of Miami, has conducted a life cycle assessment for the Halls River Bridge. It's been published in the Advances in Civil Engineering Materials. The primary authors are Thomas Cadenazzi, who was a graduate student for Professor Tony Nanni at the University of Miami, and Steve Nolan. And they have conducted both a life cycle assessment, an LCA, and a life cycle cost assessment, an LCCA, for the Halls River Bridge. I could spend an hour just talking about this talk, but this is the Cliff Notes version. Their LCCA showed that the net present value of the life cycle cost is 20% lower with FRP because of reduced maintenance and replacement costs. That's a very good story for FRP, 20% lower, but that's a story for a different day. Their LCA, which is relevant to today, their life cycle assessment, showed that the cradle to grave emissions are 26% lower with FRP than with steel. And here is the data from their LCA that shows that. I'm comparing two tables, top for FRP, bottom for steel. Here is the data highlighted for kilograms of CO2 equivalents. And if you compare this number for FRP with this number for steel, you'll see that the total kilograms of CO2 equivalents are 26% lower with FRP than with steel. And if you go across each row, you'll see that the emissions are lower at every stage. So this is not just cradle to gate. This is cradle to grave emissions are lower at every stage. This is a very good example of how using FRP with concrete can lower CO2 emissions throughout the entire life cycle. Why is this happening? Why is it lower? Well, look at when they construct the bridge. They used a Hillman composite beam. That has lower CO2 emissions than steel. They used FRP rebar, which enables you to use less concrete. That lowers FRP emissions. And then the FRP bridge has a much longer lifetime. So over the lifetime, you're going to need less concrete to replace the bridge. So you end up with a very favorable cradle to grave situation. Example number 8, let's change gears and talk about carbon pre-stressed concrete, or CPC. This is supplied by a startup company in Switzerland called CPC AG and Holcim, a concrete supplier. And they've won numerous awards. They've invested in CPC. They've won numerous awards. And this carbon pre-stressed concrete is used in things like pedestrian bridges and these platforms. So what exactly is CPC? It's not the easiest thing to find data for, but here are some things that I have found. They are reinforced with closed-meshed pre-stressed carbon wire nets. And this is a very useful picture. Picture's worth 1,000 words, showing what those nets look like. Okay, very thin carbon fibers that are embedded in a vinyl ester resin. And what this picture shows is that a CPC slab is basically the same thickness as a piece of steel rebar. Okay? So how does this lower CO2 emissions? Well, the use of those carbon microfibers to reinforce concrete enables you to make the concrete much thinner, and therefore significantly reducing CO2 emissions. And here's some example for this footbridge in Switzerland. This is taken right from their website. The footbridge made with concrete would weigh 56 tons, but with CPC, that's reduced to 14 tons. That translates into a 75% reduction in the CO2 footprint for this bridge. 75%. One last example. Let's talk about carbon cast with Seegrid. Seegrid is produced by Schomerat, and it is used with concrete. Here's a picture of Seegrid. It consists of carbon fiber in an epoxy grid, and it is typically used more in construction than in infrastructure applications. It's used in precast concrete, and it's used by members of what's called the Altus Group, a group of precast concrete suppliers. They use Seegrid to make what are called carbon cast panels, and they are used in insulated wall panels and architectural cladding, like the exteriors of the two pictures of these buildings here. Carbon cast with Seegrid. So how does Seegrid work? What role does it play? It actually can serve two functions, and I'm going to highlight them in these cartoons. It can serve as a low thermal conductivity, high strength conductor, essentially a truss that extends through the insulating foam between the two concrete widths. It can also serve as a reinforcement for a concrete width. Although it is not the primary reinforcement, rebar is the primary reinforcement, but it can be a secondary reinforcement. So again, Seegrid is used in conjunction with concrete. And how is it used? Well, Metromont, one of the members of the Altus Group, uses Seegrid to reinforce precast concrete in data centers like the one shown here. And they have found that using Seegrid can reduce the amount of concrete by 40%. 40%. And today, here in the United States, these data centers are popping up everywhere. There's a tremendous amount of concrete being used to create these data centers, and you're lowering CO2 emissions when you use C-Grid. Less concrete, less CO2. So to summarize this portion of my talk, I've shown you that the use of FRP in conjunction with concrete can result in double-digit reductions in greenhouse gas emissions. All very good examples of this simple equation that concrete plus FRP equals lower CO2. Less concrete, less cement, less CO2. All right, let's come back to my outline and talk about the landscape of decarbonization. What exactly do I mean by decarbonization landscape? Well, I could have entitled this portion of my talk, Who Cares About Decarbonization? And I want to address this because the landscape for decarbonization is definitely changing, especially in light of the presidential election in the United States last November. Because under the President Biden administration in the United States, lowering greenhouse gas emissions was definitely a priority. And that was reflected in programs at the Department of Energy, the Department of Transportation, and the EPA. However, in the President Trump administration, they have eliminated or rescinded many programs related to greenhouse gases. They basically have said they don't want to hear too much about greenhouse gases and climate change. But there is still considerable interest in decarbonization. Nearly every major construction company has published a commitment to lowering their carbon footprint. Building owners and architects are interested in getting LEED credits for using building materials that lower emissions, both lower embodied carbon and lower operational carbon. And although the United States has pulled out of the Paris Accord, there are still more than 170 countries that have signed and approved that accord, so there's definitely global interest in decarbonization. I showed you this list earlier of saying how people want to decarbonize, and I show it again here because I want to use it to cover some of these bullet points. Let's start with the first one. Nearly every major construction company has published a commitment to lowering their carbon footprint. Here's some examples of that. This is taken right from Skanska's website, and they are interested in finding low carbon solutions and building responsibly. Here's Turner Construction, again, taken from their website. Net zero emissions, reducing carbon footprint, decarbonization. I could show you many, many more examples of this, but again, nearly every major construction company has published a commitment to lowering their carbon footprint. Here are some examples from the United States: Bechtel, Kiewit, AECOM. Here are some examples from Europe. You've got WSP in the UK. You've got Hochtief in Germany, interested in low emission construction. In addition to construction companies, there's also interest in building owners and architects who want to get LEED credits. Decarbonization is a very important element of LEED Volume 5, and these folks are interested in getting LEED credits for the use of low carbon materials. So there's definitely interest. It will be very interesting to see if and how this interest in decarbonization within the construction community changes over the next several years. That's definitely something that I'm going to be monitoring. So I'm going to come back to my take-home message one more time, that the use of FRP composites can significantly lower emissions of carbon dioxide and other greenhouse gases in infrastructure and construction applications. I've shown you that that's true when they are used in place of steel. I've shown you that's true when they are used in conjunction with concrete. This is a very important message for people involved with infrastructure and construction, and it's a message that is important to deliver. And so my final take-home message is that if you want to decarbonize, if you want to lower greenhouse gas emissions, if you want to lower your carbon footprint, if you want to achieve net zero, you definitely need to be considering FRP. I want to finish up with some acknowledgments. I want to thank the Advanced Building Construction Collaboration, the Carbon Leadership Forum, and John Schweitzer from ACMA. They have all helped me move up the learning curve and understand the terminology of decarbonization. I've tried to thank several people during my presentation, but I want to give special thanks to Dustin Troutman from Creative Pultrusions and Steve Nolan for Florida DOT for help with the calculations that I've shown you. And I also want to thank members of the Infrastructure and Construction Working Group from IACME, the Institute for Advanced Composites Manufacturing Innovation, for helping me put this story together. That concludes my presentation. I'd like to thank you for your attention, and I'll be happy to answer any questions.